Welcome everyone to the 12th Madan Lal Mehta lecture of the Department of Theoretical Physics at the Tata Institute of Fundamental Research. The MLM lecture series started in 2010 when Mrs. Rani Mehta, Madan Lal Mehta's wife, gave us, presented the department with an endowment to organize an endowed lecture, a series of lecturers of the highest eminence. She envisaged that the lecturers would come through, lecture to us, and then interact with us to promote research as well as international cooperation. As I said, the lecture series has been going on from 2010 onwards. Our first lecturer was Professor Bohigas. Edward Witten will present the 12th MLM lecture to us in a few minutes. MLM lecturers are physicists of high eminence from any area of physics. Sort of to illustrate that, let me read out the names of the last 5 or 6 lecturers. In 2016, we had the statistical physicist Dov Levin. In 2017, we had the lattice gauge theorist David Kaplan. In 2018, we had the condensed matter physicist and our good friend Ashwin Vishwanath. In 2019, we had the great Indian physicist Ashok Sen. And in 2020, we had Wendy Friedman, the cosmologist, who told us that she didn't think there was a Hubble tension. And now we have, in a few minutes, we will have Professor Witten giving us the 12th MLM lecture. Before we start proceedings, there are two things I would like to do. First, I wanted to tell everyone here a little bit about Madan Lal Mehta. Madan Lal Mehta was born on the 24th of December in 1932 in a village near Udaipur in Rajasthan. He did a degree, his MSc, his master's in mathematics in the University of Rajasthan at Jaipur. And then he joined the Tata Institute of Fundamental Research for a couple of years between 1956 and 1958. In the early years of the Tata Institute, Homi Bhabha and the people working with him followed this pattern of getting bright young people and then having them at the Tata Institute to do courses for a bit, and then trying to place them in PhD programs abroad. This pattern was followed with many people, many eminent people, George Sudarshan, for instance. In line with this pattern, 2 years after joining TIFR, Professor ML Mehta left TIFR to do a PhD in Saclay in France. He did his PhD under Bloch. After doing his PhD, he spent a year at the Institute for Advanced Studies in Princeton, EDS Institute. After that, he came back to India and was, I believe, a faculty member in the University of Delhi for a few years before moving back abroad, this time to France, once again to Saclay, where he did his PhD. He first moved to the US. He spent 1 year at Princeton University, the year between 66 and 67, and then moved from there to France, to Saclay, where he spent the next 38 years or so. From 1967 to 2005, to the end of his research career, he was at Saclay in France. Then in 2005, he returned to India and passed away on the 10th of December 2006. As I mentioned, in memory of Madan Lal Mehta, Mrs. Rani Mehta presented this endowment for this lecture so we could remember him every year. Professor Mehta's work has worked on many subjects, but the work that perhaps is most prominent is work on random matrix theory. I remember as a PhD student being instructed to read his book on random matrices, and I remember the thrill of the pleasure of the beautiful writing and the simple presentation and just being able to understand so easily his work on random matrix ensembles. Among his many contributions to the study of random matrices is the invention of the orthogonal polynomial method with Godin and the work on circular ensembles with Dyson. Okay, that's all I wanted to say in the introduction. Before we proceed to introduce our speaker for today, We have one thing that is not usual in these ML Meta lectures. Before when we were planning this lecture, I contacted Mrs. Rani Mehta, who now lives in China, or at least is now in China, and requested her to join us so that she could say a few words at the beginning of this lecture. She wasn't able to join us, but she sent us a video, a couple of 2-minute video. Rishi, I would like to request you to play that video. Everyone, please put your volume up because her voice is a bit low, so you may find it a bit hard to hear.
Hello, everybody. Very glad to see you, to meet you. I'm happy to join this meeting. It is really an honor for me. So many thanks to Professor Mingwala for his kindness. Since the first meeting of 2009, more than 10 years have been passed. It is great to see that since the very beginning, the foundation runs so well and the money has been used to the point. So please accept my high respect to the present as well as all the previous lecture committees for their constant efforts. I wish a great success to this 12th lecture in memory of Madan Lal. Thank you. Thank you very much.
Great. Mrs. Mehta, apart from kindly sending us this message, also asked me to convey a message to the audience here. She said that she's spending much of her time now translating books from interesting books from India into Chinese, into Mandarin. And she's doing this because she feels that Indian and Chinese people don't understand each other very well, and she feels that if there was more material available in India and Mandarin, that would help. It would help. She's looking for suggestions of things that would be interesting to translate. So she asked me to ask all the participants of this meeting for suggestions for material to translate. If you have a suggestion, send it to me by email. I'll pass it on to her. Okay. Now, I request Professor Gautam Mandal to introduce our speaker for today, Edward Witten.
Thank you, Shiraz. It is a great honor for me to introduce Professor Edward Witten, who is one of the leading theoretical physicists of our times. Professor Witten is a Charles Simonyi Professor of the School of Natural Sciences at the Institute for Advanced Study, Princeton. He has done pioneering works in many areas of theoretical physics, especially string theory, besides doing groundbreaking work in mathematics. His work is too vast to mention here. To name just a few, his work in string theory in the 80s, with others, gave us the first glimpse that string theory not only unifies gravity with quantum physics, but with other forces and even matter. His work in the 90s showed that the 5 different consistent superstring theories were actually not distinct, but are simply different corners of the same theory called M theory. This was called the second superstring revolution and defined a new era of string theory. In the last couple of decades, his contributions to the subject of gauge gravity correspondence has provided profound insights, including a connection between black hole thermodynamics, the topic of today's lecture, and the phase structure of gauge theories. Professor Witten's work in mathematics, to quote Sir Michael Atiyah, is characterized by a brilliant application of physical insight leading to new and deep mathematical theorems. An example of such insights is his discovery of relations between quantum field theories and the topology of spacetimes. In particular, his work on Chern-Simons theories in the 80s provided a framework for understanding the mathematical theory of knots and three manifolds. Another celebrated result of his was the proof of the positive energy theorem in general relativity using supersymmetry, which earned him the Fields Medal in Mathematics in 1990. Professor Witten can truly be called a complete theoretical physicist, as can be seen from his contributions in other areas, which range from topological phases of condensed matter physics, phase transitions in cosmology, and theories of dark matter, etc. Professor Witten has received numerous awards and honors. To mention just a few, he has received the MacArthur Fellowship Award, the first Dirac Medal, the Albert Einstein Medal, the Fields Medal, the Poincaré Prize, the Isaac Newton Medal, and the Fundamental Physics Prize, among many others. His impact and influence can hardly be measured in terms of these awards, though. He has given numerous fascinating interviews and public talks, including those at Strings 2001 and 2015 held in India, which many of us here have had the opportunity to attend. These talks have been inspirational to whole generations of people. His description of strings and particles as analogous to a symphony orchestra and a tuning fork is nothing short of poetic, while remaining scientifically accurate. The level of his influence can be gauged by the fact that the Time magazine once named him among the 25 most influential Americans. Personally, I was fortunate to be a postdoc in Professor Witten's group for 2 years, 1989 to 91. After growing up during my graduate school years, being inspired by his amazing papers, it was a wonderful experience for me to be able to interact with Edward in person and receive his guidance and encouragement. It is a great honor for me to invite Edward to deliver the Madan Lal Mehta lecture on black hole thermodynamics then and now.
Thank you. So Gautam, thanks very nice for that very kind introduction. The only problem is that I probably can't give a lecture that will live up to the introduction, but I'll have to do what I can. Sorry. The trouble with stopping screen sharing before the lecture is that starting it again. Sorry. Okay. You can see the screen, right?
We can see the screen, yes.
Okay. Now I can see it too. The problem was that you were seeing it, but sorry, this is the, sorry.
Yes, it's perfect. We can see it well.
Well, it wasn't perfect because I somehow was the wrong file.
Ah.
I had opened the right file before. I'll have to start over. Sorry. Okay. What happened was that when I ended the test screen share, I inadvertently closed the file completely. So anyway, as I said, thanks very much, Gautam, for the kind introduction, which unfortunately I will probably not be able to live up to with this lecture, but I'll do what I can. So the talk will come in two parts. The first half, I'll explain some of the key points of black hole thermodynamics from the classic period when it was developed in the 70s by Bekenstein, Hawking, and others. In the second half, I'll explain some more contemporary results, though it won't be possible in one lecture to bring the story up to date. Unfortunately, I can't explain the high points, not all of them, in either half of the talk. When I was planning this talk, what I really wanted to do was to explain the second half, where understanding black hole thermodynamics requires a more precise knowledge of what entropy means quantum mechanically. But I didn't want to assume everyone was familiar with the basics, so I wanted to give the first half of the talk as well. Anyway, it ends up that it's pretty hard to do all this in one lecture. Black hole thermodynamics started with the work of Jacob Bekenstein, then a graduate student. His advisor was John Wheeler, And he was inspired by Wheeler's questions about what the second law of thermodynamics means in the presence of a black hole. So for an ordinary system, the second law says that the entropy can only increase. But if we toss a cup of tea into a black hole, the entropy seems to disappear. Bekenstein wanted to generalize the concept of entropy so that the second law would hold even in the presence of a black hole. For this, he wanted to assign an entropy to the black hole. Well, he needed a property of a black hole that can only increase. For example, the mass of the black hole will not do. It's not true that the mass always increases. If you have a spinning black hole, it's possible for its spin to slow down, and then the mass of the black hole also reduces. In fact, it's believed that that's the mechanism by which black holes at the centers of galaxies power the jets that we see coming out of the galaxies. So the mass of a black hole isn't a good candidate for the entropy. But there is a quantity that always increases. Following earlier work on special cases by people like Christodoulou, Stephen Hawking had just proved the area theorem, which says that the area of the horizon of a black hole can only increase. So it was fairly natural for Bekenstein to propose that the entropy of a black hole should be a multiple of its horizon area. For example, I've written the metric for a Schwarzschild black hole of mass m. The horizon is at r equals 2 gm, and the horizon area is the usual 4 pi r squared for a sphere of radius r, which works out to the 16 pi squared g squared m squared, where g is Newton's constant, and h bar and c will be 1 in our units. Well, since entropy is dimensionless, to relate the entropy of a black hole to its area, you need a constant of proportionality with dimensions of area. From the fundamental constants h bar c and g, you can make the Planck length, which is this incredibly tiny length, and therefore the Planck area LP squared. So in units where h bar and c are 1, LP squared is just Newton's constant g. And Bekenstein's formula for the area, for the entropy, was that it was the area over a constant times g, where the constant was not clear in Bekenstein's work and was provided a few years later by Stephen Hawking in a way I will explain. So for a Schwarzschild black hole using the formula we worked out for the area, this is the entropy of a Schwarzschild black hole, and it's huge. For example, a black hole with the mass of the sun has an entropy that's something like 10 to the 20 times the actual entropy of the sun. Bekenstein's idea was that the entropy of a black hole was supposed to capture information lost when the black hole was formed. He interpreted it as the logarithm of the number of ways the black hole might have formed. And he proposed a generalized second law saying that the generalized entropy can always increase. Here, what I've called S out is the ordinary entropy of matter and radiation outside the black hole. The second part of my talk is going to be devoted to an explanation of what S out should really mean at a more fundamental level. But for now, following Bekenstein, it's just naively is the ordinary entropy outside the black hole. So the generalized entropy is the area over 4g plus the ordinary entropy that you can see as an observer outside the hole. The claim is that when something falls into the black hole, the ordinary entropy may go down, but the area over 4g increases by more. So Bekenstein made a few tests trying to show that that was true. So here's perhaps the most interesting. We shine photons with a wavelength lambda, therefore energy 1 over lambda, on the black hole. The entropy of a single photon is of order 1, for example, because the photon has 2 polarization states. When the black hole absorbs 1 photon, its mass changes by delta m, which is 1 over lambda, the photon energy. So its entropy therefore shifts by this amount, which to first order in the photon energy is what I've written here. I just kept the term linear in 1 over lambda. Bekenstein wanted the increase of the black hole entropy to be bigger than the absolute value of the change in the outside entropy. When the black hole absorbs a single photon, the S out goes down by an amount of order 1. So he wanted the black hole entropy to increase by more than 1. Well, he observed that if the black hole is capturing a photon whose size is smaller than the Schwarzschild diameter of the black hole, say the wavelength is much less than 4 GM, that the change in the black hole entropy is much bigger than 2 pi squared, which is satisfactory. It's more than the change in the outside entropy, which was close to 1. He did a more complete calculation for a rotating black hole and got a result with a smaller constant, but still satisfactory. However, Bekenstein did not get a satisfactory answer if the black hole is absorbing photons of wavelength larger than the black hole size. The problem is that a very large wavelength photon still has an entropy of order 1, but its energy can be arbitrarily small. So when the black hole is absorbing photons of very long wavelength, he did not get a sensible answer. What he wrote about it was not entirely convincing, in fact. The question really does not have a satisfactory answer in the framework Bekenstein was assuming, which was that whatever falls behind the black hole horizon stays there forever. In thermodynamic terms, since Bekenstein assumed that the black hole does not radiate, one should assign to it a temperature of 0. Thermodynamics says that at equilibrium, the changes in energy E and entropy S satisfy dE equals T ds, or ds equals dE over T. So a system with T0 should have ds equals infinity if dE is non-zero. But Bekenstein wanted the black hole to have a finite, not infinite entropy and a 0 temperature, while still being able to have a non-zero dE. So these properties were kind of contradictory and kept him from getting a completely satisfactory story for his thought experiment for the case that the photon wavelength was extremely large. The problem is that you can't analyze the absorption of very long wavelength photons by the black hole while ignoring the fact that, as we learn later from Hawking, the black hole is strongly emitting such photons. Famously, Stephen Hawking discovered shortly later that at the quantum level, a black hole is not really black. It has a temperature proportional to h bar. It said that Hawking thought Bekenstein was wrong and was trying to disprove Bekenstein's claim and ended up proving it. Hawking discovered this by analyzing the behavior of quantum fields in a black hole geometry. So here I've drawn a Penrose diagram that describes the collapse of a star into a black hole. I hope most of you are familiar with the basics of Penrose diagrams because I won't be able to give a proper explanation. This is a diagram, the angular directions are suppressed, and this diagram is a two-dimensional diagram where the distance from the center of the black hole runs horizontally and time runs vertically. In this picture, a light ray travels at a pi/2 angle to the vertical. And this outer edge is what's called past null infinity. That's where light rays could come in from. Light rays go out, emerge at future null infinity out here. A massive particle would exit the diagram at this point, future infinity. The black horizontal line is the horizon of the black hole. The red shows the trajectory followed by a collapsing star. It came from the far past, lived for a while, and then collapsed behind the black hole horizon. An observer at infinity, we want to imagine the world as it looks to an observer in the far future at spatial infinity. Such an observer is way up near the corner of this diagram. This black line is Penrose's way to depict future infinity. But we want to be not just in the future, but in the far future, which means way up near this corner. So an observer seeing the star before it collapsed would see a photon maybe emitted here, going off at a pi/2 angle, and arrives here. Later, the star emits a photon that arrives at future infinity up here. And the very last glimpses of the star, before it crosses the horizon and disappears, are seen by an outside observer way up near this corner. That's the classical picture, and Hawking described the quantum corrections to it. Now, measurements that an observer at future null infinity can make can be traced back to initial conditions of the quantum field on a Cauchy hypersurface, which is a technical phrase for an initial value surface. So here in this picture, I've drawn an example of a space-like surface that crosses the horizon. It crosses the horizon to the future of the collapsing star. So where this Cauchy surface is crossing the horizon, the star is long gone. The surface, if you continue it behind the horizon, does cross the collapsing star. But the outside observer only sees the portion of this Cauchy hypersurface that's outside the horizon and to the future of the star. So whatever the observer up here will observe can be traced back to initial values on a surface that's effectively in vacuum. It's in the vacuum to the future of the star after the star has already collapsed. So Hawking did a calculation. Well, what I'm describing is a slight improvement of Hawking's calculation by later physicists such as Unruh and Turing, Haag and Turing. In this version of Hawking's calculation, you only have to study the behavior of the quantum fields in the vacuum where there's no star, because the star has already collapsed and disappeared. So in this picture, this is the same picture again, but the purple lines, which are meant to be at a pi/2 angle to the vertical, show light rays leaving the initial value surface somewhere close to the horizon and arriving at future infinity somewhere. The important point in this picture is that the light rays that arrive late for the future observer have started very close to the horizon. So what will the observer see? Part of Hawking's insight was that although the full details of exactly what the observer will see depends on the details of the collapsing star, if we ask what the observer will see in the very far future after transients die down, there's a universal answer. The reason there's a universal answer is that what we see can be traced back to initial data on this surface after the star has collapsed. And this, I drew a surface we could use, but I could have drawn a later one. We can trace back our observations to initial data on a surface that itself is as far future as we want, in the future as we want, compared to the primary event that caused the black hole, brought the black hole into being in the first place, which was the collapse of the star. Now, the most important point, as I keep telling you, is that a signal that's received very late originated very close to the horizon. That means that observations made at late times depend on measurements of the state of quantum fields in a very, very tiny span of distances very close to the horizon. But every state is indistinguishable from the vacuum at short distances. That's a basic property of quantum theory. So the late time observations of the observer probe the vacuum state near the horizon at short distances. If you've studied quantum chromodynamics, the theory of strong interactions, you've probably met the idea that the total cross-section in E plus E minus annihilation probes the strong interaction vacuum at short distances, and that's why there's a simple answer. But the Hawking process probes the vacuum at much shorter distances than we can really reach in E plus E minus annihilation. Incredibly short distances, exponentially short distances, as I'll explain in a moment. So Hawking got a simple answer for the late time behavior, regardless of how the black hole formed, because it only depends on what's happening at incredibly short distances near the black hole horizon. So here's another picture where I'm only showing the relevant part of the picture now. So a small portion of the initial value surface near the horizon, it's parameterized by coordinate u. It doesn't matter what coordinate you use. Then t is the time of the distant observer who's making measurements on this black line up here, right up near the corner. So t is the time at which the observer detects a signal, and u is the distance from the horizon at which the signal was emitted. Now, there's a small calculation you have to do to show the relation between u and t. I'd wanted to do it using the Schwarzschild metric to calculate this, but one of the compromises I found I had to make in planning the lecture was to skip this calculation and just write down the answer. The answer is that as u goes to 0, t becomes logarithmically large. You find this formula by solving the geodesic equation for an outgoing null geodesic. Now, the formula doesn't depend much on how you define u. If you rescale u, that will add a constant that will shift the constant C0, but that constant will be unimportant. And nonlinear changes in u will make even less important corrections to the formula. So there was no natural choice of the u coordinate near the horizon, but what we're going to say doesn't depend on what coordinate you use. Now, since t only grows logarithmically relative to u, that might not seem so extraordinary, but if you solve for u, then u is exponentially small for large t. So, for example, if you have a black hole, which is the mass of the sun, and you wait 1 millisecond, after 1 millisecond, this exponent is minus 1,000, and u has become e to the minus 1,000 times something of order 1. So in the case of a black hole with the mass of the sun, merely waiting a millisecond makes u incredibly, incredibly small, much smaller than anything you would ordinarily talk about in physics. So that's what I mean when I say that measurements at late time, where late could mean just after a millisecond for a solar mass black hole, you're probing distances incredibly close to the horizon. And likewise, du dt is exponentially small, as you see if you differentiate this with respect to t. So a mode observed at infinity will have undergone an incredibly large redshift on its way. So a mode of given energy E that we observed at a late time originated from a very high energy mode near the horizon. And that's why there's a simple answer. A mode of very high energy propagates freely along an outgoing geodesic. So what is the observer at infinity going to measure? Well, let's say the observer at infinity measures a quantum field psi of t to probe the radiation. The typical observer is a two-point function. For example, the observer might want to know how many photons there are in the outcoming radiation. That's a two-point function of an operator that creates and annihilates photons. Or if you want to know correlations among outgoing photons, you'd measure a four-point function and so on. Near the horizon, two dimensions are important, the two I keep drawing in this picture. We could get rid of the angular coordinates by going to a particular partial wave in the angular directions. So we effectively have a two-dimensional problem. In the two-dimensional problem, if for simplicity psi is a free fermion of dimension 1/2 in the 1 + 1 dimensional case, then near the horizon we would have had this formula for the two-point function. But if I express it in terms of the coordinate of the observer at infinity using this formula, the change of variables from the two-point function near the horizon to the two-point function seen at infinity gives this. And that's actually a formula for a thermal two-point function, which you see because it's anti-periodic in imaginary time. It's odd under t shifted by 8 pi gm times I, the square root of -1. It's anti-periodic because I wrote formulas for a fermion. So the anti-periodicity corresponds to the fact that this is a thermal correlation function at a temperature which is the inverse of the period, or in other words, 1/8 pi gm, which is the Hawking temperature. So in other words, a black hole after transients that depend on how it was created die down, radiates thermally at a temperature 1/8 pi gm. Now, this explains why Bekenstein had trouble making sense of the interaction of the black hole with low energy photons. Where he had trouble was for photons whose energy was less than the Hawking temperature. So the black hole was emitting photons of that type in large numbers, and it isn't sensible to study the absorption without studying the emission. We can also now confirm the value of the entropy. Since dE is TdS, where E is equal to the mass of the black hole, and using the Hawking temperature for T, we get ds to be 8 pi gm dm. So we get S equals 4 pi gm squared. And bearing in mind the area of a Schwarzschild black hole, we get the entropy to be A/4g. So that's how Hawking confirmed Bekenstein's ansatz and determined the constant that was unclear for Bekenstein, and also resolved the trouble Bekenstein had with the long wavelength photons. Now, going back, I want to tell you how I cheated here. I cheated principally, well, I didn't explain the gray body factors, which come up in a more complete calculation. And the way I cheated slightly was that I claimed that the signal propagates freely outward because of its high energy. The more accurate statement is it propagates freely outward until it reaches a wavelength comparable to the size of the black hole. At that point, subtle quantum effects are no longer important, but there is a non-trivial classical effect that you have to take into account, leading to Hawking's gray body factors. Anyway, one of the compromises to give the lecture was to cheat and not explain the gray body factors. Now, many researchers, and really going back to Bekenstein, have thought that somehow the entropy A over 4G means that the black hole can be described by some sort of degrees of freedom that live at its surface, with 1 bit or qubit for every 1 over 4G of area. For example, John Wheeler, who had been Bekenstein's advisor and probably inspired much of it, in a famous article in 1992, illustrated that idea with this picture. He drew a picture of the horizon of a spherically symmetric black hole, and he sort of covered it with little quadrangles that are meant to have constant area, 1 over 4G, and then drew a bit 1 or 0 in each quadrangle. And that was supposed to illustrate the idea that the entropy is 1 for every 1 over 4G of area. This picture is still aspirational today, though. We don't have a good precise understanding of something similar to that picture. Now, a fundamental point about Hawking radiation is that the radiation appears to be thermal, even though the black hole could have formed from a pure state. Remember, the calculation we did, well, first of all, the calculation we did was totally agnostic to how the black hole formed. The black hole had long disappeared behind the horizon before we set up this initial value surface and did this calculation. So whether the black hole was in a pure state or a mixed state or what pure or mixed state it had been had no bearing on this calculation. This calculation instead considered quantum fields that actually were in a pure state, but it was a pure state on both sides of the horizon. What we did was we made measurements only outside the horizon. And what we learned, or what Hawking learned, was that if you make measurements only outside the horizon, then your measurements will appear to be thermal. So you see, the observations of the distant observer amounted to observing a quantum field that lives in 1 + 1 dimensions on only half of space. Here I've drawn a line, which I've depicted as if it's a line in space at time 0. But you should think of it as being corresponding to that initial value surface that went through the horizon. I've drawn in thicker the x greater than 0 part of the line, which I'll assume we can observe, and thinner the x less than 0 part of the line, which I assume we won't observe. The essence of the Hawking effect is that if you observe a quantum field only in half of space, your observations will be effectively thermal because of entanglement of degrees of freedom that you observe with degrees of freedom that you can't observe. So I want to give a short explanation of this. And to do so, this explanation goes back to Unruh and others in the 1970s. To do so, we think of the ground state of a quantum field. Well, we think of the quantum field as a function 5x. So the quantum state of a quantum field is a function psi of functions 5x. Sometimes it's called a functional psi of the function 5x. And moreover, we'll think of 5x as a pair, which I call phi right of x and phi left of x. Phi left is simply the values of the function on the left half. Phi right are the values on the right half. Of course, there's a constraint that they agree at the boundary between the two halves, but because of quantum fluctuations, that constraint doesn't do much. We'll think of the ground state as a function psi of phi left and phi right. And we want to discuss how to make a density matrix appropriate for observations of phi right only. I'm going to take a moment to remember the general idea of a density matrix. We start with a Hilbert, what's called sometimes a bipartite or tensor product Hilbert space. The Hilbert space HA tensor HB, that's the tensor product of two factors. Then we take a state psi AB that we could assume is a pure state. We first make the pure state density matrix which is just the projection operator onto the state psi. If O is an operator, its expectation value in the state is the same thing as the trace of O times this pure state projection operator. Now, this pure state density matrix is the orthogonal projection operator to the state psi. In particular, it's Hermitian non-negative, has trace 1, and it also has rank 1 because it projects onto a single state. Now, suppose we're only going to observe the subsystem A. That means we only consider operators, OAB, that act as something on A times the identity on B. So now we want to calculate the trace in this density matrix rho AB, OA tensored with the identity. Well, a trace means you sum over all states of the A system and all states of the B system. But here, the sum over the states of the B system is trivial because the operator on the B system was the identity. So if we do what's called a partial trace, where we take rho AB, but we sum it over all states of the B system, we can get what's called a reduced density matrix rho A for the A system, such that the expectation value of an operator that only involves system A only depends on the density matrix of system A. So in general, in quantum mechanics, to describe a subsystem, you need to use to give the most economical possible description of a subsystem, ignoring the rest of the universe, you should use a density matrix rho A for that subsystem. So that's what I said in the sentence. For measurements on system A, you can use the density matrix rho A obtained from rho AB by taking a partial trace on HB. The definition of rho A ensures that it's Hermitian non-negative and has trace 1, just like rho AB. For example, if you take the trace of rho A, that'll mean you'll finish taking the trace of rho AB, you'll get 1. But rho A will generically not have rank 1. If psi AB is what's called an entangled state of the subsystems A and B, then rho A has rank greater than 1. An entangled state is just a state that's not a tensor product of separate pure states of the two subsystems. So almost every quantum state of the combined system is entangled. To imitate this in field theory, we first need a convenient representation of the ground state wave function, psi. It's given by a path integral on the lower half plane with boundary conditions in which the boundary values, see, psi depends on phi left and phi right, values of the quantum field in one dimension. The one dimension is drawn in solid black. The black dot divides the right half. So phi right is the value here. Phi left is the value here. And to compute this functional psi of phi left and phi right, Feynman and his successors tell us to do a path integral, Euclidean path integral over the gray region, which is half space to the past, to the infinite past of the line in which we're trying to define the wave function, with boundary conditions in which the boundary values phi left and phi right on the boundary are specified. The path integral computes a wave function psi of phi left and phi right, which is the ground state wave function. Now, if we want to make a density matrix, the pure state density matrix, we multiply a bra by a ket. Well, I just told you how to calculate the bra, and the ket is the same picture flipped over. Well, in this notation, the bra and the ket are obtained by flipping from left to right. In this picture, you flip from bottom to top. So one of them is a path integral on the lower half plane. The other is a path integral on the upper half plane. Now, the partial trace that gives a density matrix for the right half only is accomplished by setting the fields phi left and the left halves of the picture to be equal and integrating over phi left. So in the picture, you do that by gluing the two left halves together. If you want the value here to be the same as the value here, there's no reason to draw them separately, just glue them together. But I impose no similar constraint on the right. So the path integral looks something like this. Now we're doing a path integral on the whole plane, but with a slit along the positive x-axis. So I've drawn an angle so you can see it, but this is simply the whole plane, and we made a cut on the positive x-axis. The cut starts at x equals 0. So a path integral on the cut plane gives the density matrix, which is a function of a pair of phi rights, phi right and phi right prime, where phi right prime are boundary values above the cut and phi right are boundary values below the cut. That's the density matrix for an observer who only makes observations on half of the line. But we can understand this path integral in another way. I'm going to draw this picture again. See, this picture represents the whole plane with a cut. And the whole plane has rotational symmetry, but not exhibited in this picture. I'm just drawing the plane again in a way that makes it obvious that it had rotational symmetry that was broken by making the cut. Now, you can generate the cut plane if you start with a half line and rotate it by a 2 pi angle around the endpoints. So to make the density matrix, you can start with a quantum state on a half line, and then you act with e to the minus 2 pi times the matrix that propagates it in the fashion of this rotation. So that gives a formula for the density matrix. If R is the operator that generates the rotation, the density matrix is e to the minus 2 pi r. This is a very important formula. It's one of the rare cases in quantum field theory that you can get a useful, simple result for a density matrix for a quantum field. It's useful to write the formula in Lorentz signature. So the operator that rotates what in Euclidean signature is a rotation of the xt plane, in Lorentz signature becomes a Lorentz boost of the xt plane. So in Lorentz signature, R becomes the Lorentz boost generator K, and the density matrix is e to the minus 2 pi K. However, since rho is a density matrix defined on a state, acting on a state defined only on the positive half line, say x positive, likewise here, K is a Lorentz boost generator that only boosts the quantum fields where x is positive. So I've written the standard formula for a Lorentz boost generator, except I started the integral at 0 instead of at minus infinity, because we're only applying this boost to the fields we're observing, which are at positive x. So we're going to need this formula in a little while, so let's remember it. That's the formula for the density matrix of a quantum field where you only make observations in half of the space. So now we go back for a moment to our formula relating the time at which you make an observation to the distance from the horizon at which the signal originated. We can give a new explanation of why this formula led to a thermal density matrix. Observations made near future infinity are equivalent to observations made near the horizon in the region with U positive. That means that our discussion applies, and in terms of U, the density matrix is the exponential of minus 2 pi times K. Let's convert that to what observer at infinity would say. The Lorentz boost operator acts on U by U d by du. So using this formula, we see it acts on T as minus 4gm times d by dt. So the mapping from U to T maps K to 4gm times the Hamiltonian, and the density matrix, e to the minus 2 pi K, becomes e to the minus 8 pi gm times h. And that's a thermal density matrix at the Hawking temperature. I'm sorry if I rushed through that one too quickly, but what I wanted to say was that if you take a Lorentz boost of U, you'll find that it's equivalent to a time translation of T. And the fact that the density matrix is the exponential of minus 2 pi times the boost operator translates it to being e to the minus something times the Hamiltonian, where the something is the inverse of the Hawking temperature. Now, there's a lot more to say about this story from the 70s. With time, I would go on to explain the Euclidean picture of black hole thermodynamics that was developed by Gibbons, Hawking, and others. But that would come at the cost of not being able to give even a taste of the modern results. Progress in the 21st century has largely depended on understanding the meaning of quantum entropy at a deeper level. Now, with one lecture, I'm really only going to be able to explain one result in this direction, which was by Horacio Cassini. We need to begin by discussing more thoroughly what entropy means at the quantum level. The original definition of entropy in terms of microphysics was by Boltzmann in the 19th century. He considered a system of n particles in a box with positions x and momenta p. As a classical physicist, Boltzmann assumed that at a given time, x and p have definite values, even if we do not know them. He described the state of our knowledge by a probability distribution function, rho of x and p, that encodes our knowledge, and after great labor, he defined the entropy as the phase space integral of minus rho log rho. For a quantum system, the density matrix rho, which we introduced earlier, is the closest analog of the classical probability distribution function. Recall that if a system has density matrix rho, then the expectation value of any observable O is the trace of rho times O. After diagonalizing the Hermitian matrix rho with eigenvalues lambda j for some lambdas, we find that the expectation value of O is the sum of lambda I times the matrix element of the operator O in the state I. So all expectation values are as if the system is in the state I with probability lambda I. So the eigenvalues of the density matrix are classical probabilities, or the closest analog of classical probabilities, and rho is the closest analog of the classical probability distribution function. Notice that since rho is non-negative and its trace is 1, the lambdas are non-negative and their sum is 1. So it does make sense to interpret them as probabilities. So the quantum analog of Boltzmann's integral is the von Neumann entropy of a density matrix, given by this formula. That's the best quantum definition of entropy. In the classical limit, the von Neumann entropy goes over to the classical entropy times a constant that classically is poorly defined. You see, this dp dx is not dimensionless. So Boltzmann's integral did not have a natural overall normalization. To make it dimensionless, you should divide by 2 pi h bar for each degree of freedom. But of course, Boltzmann didn't yet know about h bar. So Boltzmann's integral had an ill-defined overall normalization. The von Neumann entropy goes over to the classical answer with a well-defined normalization. If the eigenvalues of rho are the lambdas, then the von Neumann entropy is the sum of minus lambda log lambda. So the state of a system is known with certainty if one of the lambdas is 1 and the other is 0, which means that rho has rank 1. In that case, the formula for the entropy says that the entropy is 0. Otherwise, every lambda makes a positive contribution and the entropy is positive. Now, if a system is entangled with something else, rho has rank greater than 1, and therefore the entropy is positive. So there's a fundamental difference between the classical and quantum cases. Classically, you assume that x and p have actual values. You use a distribution function only because of lack of microscopic knowledge. Quantum mechanically, even if we have as full a description of the state as quantum mechanics allows, it can still have a mixed density matrix with a non-zero microscopic or fine-grained entropy. That happens because of entanglement. If A and B are two quantum systems in an overall pure state, if the pure state is entangled, then the density matrix rho A of system A has rank greater than 1, and system A has a positive von Neumann entropy. And there's no way to avoid it. The most complete description of the system quantum mechanics would allow attributes this positive entropy to A. If A and B are entangled, this can be verified experimentally, and there's no way to describe system A by pure state density matrix with 0 entropy, because then you'd get the wrong answers for joint measurements of systems A and B. Now, just as classically, in general, our knowledge of the state of a system might be less complete than quantum mechanics allows. In that case, we describe a system by density matrix rho that reflects our knowledge. For example, if we know nothing about the state of a system, we would take rho to be a multiple of the identity, even though someone else who maybe knows how the system was prepared would describe it by a pure state. If we know nothing about a system except its temperature, we use a thermal density matrix. In such a situation, the von Neumann entropy is the thermodynamic entropy, a familiar concept classically. What's different about quantum mechanics is the entropy that remains if our knowledge of the state of a system is as complete as quantum mechanics allows. That's been called entanglement entropy because it results from entanglement with some other system, and it's also been called fine-grained entropy. The idea that the Bekenstein-Hawking entropy of a black hole should be understood in terms of entanglement entropy was apparently first put forward by Raphael Sorkin in 1983 in a paper that attracted only modest attention at the time. The idea was just the following. In a quantum field theory, divide space into regions A and B. Let psi be the vacuum state and rho A the reduced density matrix of the vacuum for the state psi. You can try to calculate the fine-grained entropy S sub A. You find that it's ultraviolet divergent, but the coefficient of the divergence is proportional to the area A of the boundary between regions A and B. Sorkin's idea in modern language was that somehow gravity cuts off the divergence, leaving an entanglement entropy in the vacuum between the two regions, and this is supposed to be the Bekenstein-Hawking entropy A over 4G, where A is the area of the boundary between them. That makes a lot of intuitive sense as it matches two ideas. One is that A over 4G is the irreducible entropy for someone who has access only to the region outside the horizon. So Sorkin says, let it be the vacuum, but if you only can see region A, you'll have an entropy proportional to the area. And two, the divergence in the entanglement entropy is proportional to the area because it comes from short wavelength modes near the horizon, as if after cutting off the divergence, the density of quantum degrees of freedom on the horizon per unit area is what Wheeler had suggested. Well, actually, Wheeler drew this picture, as far as I know, after Sorkin, but probably had been drawing similar pictures for 20 years. So let's say as Wheeler had suggested. Now, 21st century developments have supported the intuition in these statements, though leaving us with plenty of mysteries. I'd say leaving us mostly with mysteries. I'll use the remaining time, and I hope the amount of remaining time is positive, to explain just one example where something really informative has been said, which depends on a better understanding of what we should mean by entropy. And this involves the work of Cassini on the Bekenstein bound. So Bekenstein, well, I'll tell you about something Bekenstein said in 1980, but it was really, much of it was very close to what he had said in 1972. He considered whether the generalized second law is obeyed when a black hole of mass m and therefore radius r equals 2gm. Well, I've written the formula for the Schwarzschild case, absorbs a body of size curly r, energy E, and entropy S. The entropy S of the body disappears. So the generalized second law says that the increase in the black hole entropy must be more than that. The black hole entropy A over 4G changes as we actually computed in an earlier discussion of Bekenstein's first paper by this amount. So we'd like this to be true if the black hole can absorb the given body. Now, if you naively say that a black hole of a given size can only absorb a body that's no bigger than that, then the desired inequality becomes this. And Bekenstein observed the nice fact that Newton's constant doesn't appear in this inequality. So he proposed that this inequality would just be a statement about ordinary quantum physics without gravity. So this was a striking attempt to use the existence of gravity in black hole thermodynamics to make a statement that was supposed to be a statement about ordinary quantum systems that we supposedly understand without worrying about gravity. Now, my explanation didn't do justice to Bekenstein's argument that involved a highly rotating black hole and gave a somewhat more convincing explanation with better constants. I'm going to interpret the Bekenstein bound as being the statement that in quantum field theory without gravity, there should be a universal inequality between the size, energy, and entropy of a system of the general form, size times energy is bigger than a constant times entropy, with a universal constant K. Now, Bekenstein made a proposal for K, but which I think even turned out, in a sense, to give the right answer. But I'll just state it like this, that there should be some constant in this inequality. Now, faced with a conjecture like this, there are two questions you'd probably ask. Well, one question is it true? The other question is, if it's true, is it interesting? Now, for years, there was ample basis for skepticism on both counts. In fact, I was personally extremely skeptical on both counts. On the question of whether the Bekenstein bound was true, there seemed to be a trivial argument that it could not be true, at least not as a universal statement about all quantum field theories. Consider a theory that has n elementary particles, all of the same mass. Such theories exist. For instance, free field theories are good enough for this. Consider a system consisting of a box with one of these particles inside it. The box isn't important, a region of space with one of these particles. The entropy seems to be at least log n from the choice of one of n possible particles to put in the box. On the other hand, the size and energy of the box and the particle in the box do not depend on n. So it seemed clear that entropy could be arbitrarily big while keeping size and energy fixed. So it seemed clear that the Bekenstein bound could not be a universal statement about quantum field theory. On the other hand, if true, is the Bekenstein bound interesting? Okay, so let's forget about abstract quantum field theories where n can be arbitrarily big and maybe ask about the real world. So if somebody has an inequality that is always satisfied with an incredibly large margin, it might not seem very interesting. Can we think of a system where the Bekenstein bound is challenging? Is there any system that challenges the Bekenstein bound? Well, let's consider a system made mostly of massless particles. We could use massive particles, but that would increase the energy without increasing the entropy, so it goes in the wrong direction. Trying to make energy times size small for a given entropy, or make entropy large for given energy, we use massless particles. For example, consider a box of size rho containing a gas of massless particles at temperature T. In 3 space dimensions, the number of particles in the box is of order rho T cubed. The entropy is of the same order. On the other hand, the energy is rho cubed T to the 4th times a constant. So the Bekenstein ratio, S over rho times E, on which we want an upper bound, is of order 1 over rho times T. Now, if rho times T is much bigger than 1, the notion of a thermal gas in a box makes sense. In that case, S over rho E is much less than 1, and the Bekenstein bound is satisfied by a wide margin. So this is an example of what I mean by the Bekenstein bound not being too interesting. For the concepts used in the bound, like entropy, to make sense, rho times T has to be much bigger than 1. And therefore, to the extent that the bound makes sense, it isn't very challenging. The quantity that should be at least, at most of order 1 is parametrically small when the statement of the bound makes sense. Now, can we find a system for which the Bekenstein bound is interesting as well as true? While keeping still many particles in the box, but assuming the particles are not in thermal equilibrium, makes things worse, since it lowers the entropy for given energy. To make the Bekenstein bound challenging, we should reduce the number of particles, which we can do by lowering the temperature. The best case is that the box contains just one or a few massless particles, or equivalently has a temperature comparable to 1 over the size of the box. But a box containing just one or a few massless particles will weigh much more than the particles it contains. In estimating the Bekenstein ratio, we can't ignore the mass of the box, which might have been unimportant when there were many particles in the box, but it's important if the box is almost empty. Including the mass of the box goes in the wrong direction and makes the bound uninteresting. So in other words, the case that the Bekenstein bound is interesting is the case of a single particle without a box. But what does the Bekenstein bound make? What sense does the bound make in that case? In other words, what's the entropy of a single particle? For that matter, what's the size of a system consisting of a single particle? In other words, when we try to go to a regime in which the Bekenstein bound is interesting, the statement of the Bekenstein bound does not seem to make sense. Now, amazingly, Cassini was able to give a precise definition to the terms in the Bekenstein bound and to prove it. To explain this, I need to tell you one more thing about density matrices. Let sigma and rho be two density matrices on the same Hilbert space H. Then there's an important quantity called the relative entropy between the two density matrices. It's defined as the trace of rho log rho minus rho log sigma. It measures, in a sense that turns out to be useful, how different are rho and sigma. But today won't be the right occasion for telling you systematically the properties of the relative entropy. I'm only going to make use of one property, which is that rho of sigma, S of rho relative to sigma is non-negative and vanishes only if sigma equals rho. I'm going to tell you what you have to do to prove it, but I won't completely write the proof in front of you. First, sigma and rho were non-negative Hermitian matrices. So a convex linear combination of them has the same property. So pick a real number t between 0 and 1, and let sigma of t be this linear combination of rho and sigma with coefficients that add up to 1. So sigma of t is also a density matrix. So we could define f of t as the relative entropy between rho and sigma of t. Well, it's 0 if t equals 0, because then sigma is equal to rho, and this is trivially 0. And with a little calculus, you'll show that f prime of 0 is 0, and that f double prime is positive between 0 and 1. If you treat rho and sigma as commuting numbers, you'll find it completely trivial to differentiate once or twice and get these statements. But rho and sigma are actually in general non-commuting matrices. And so you have to be more careful with the calculus. However, if you try it, and I do recommend this exercise, you'll be able to prove the statements I made about this function f of t. Now, a function that starts at 0, its first derivative is 0, its second derivative is positive. It's positive when you get to 1, and therefore the relative entropy. See, f of 1 is what we want, therefore f of 1 is positive. So I see I've written in parentheses a comment that's made to help you do the calculation for non-commutative matrices. For numbers, you would just differentiate naively, to take into account that you're dealing with that rho and sigma don't commute. You might find it helpful before trying to differentiate to use this representation of the logarithm. Now, Cassini applied this to the case of two states of the quantum field theory. One state is the vacuum, and the other state is any state psi. You see, why do we have to consider any state? I hope to have shown you that when you can apply thermodynamics, the Bekenstein bound isn't interesting. And therefore, to make sense of the Bekenstein bound, you have to use concepts that apply to a completely arbitrary quantum state, whether or not you would usually think thermodynamics is applicable. And therefore, you need to use a notion of entropy that makes sense for an arbitrary quantum state. So it's going to have to be the fine-grained quantum entropy. So since the Bekenstein bound is only going to be interesting when thermodynamics isn't applicable, Cassini had to use concepts that go beyond ordinary thermodynamics, where nevertheless meaning could be attributed to entropy. So the goal is to prove that the Bekenstein bound is valid for the state psi with the correct interpretation of the terms. First, Cassini picked one of the spatial coordinates that he called x, and he divided space into two halves, positive x and negative x. The corresponding division of space-time looks like this in a two-dimensional picture where I only show x and the time t. So there are transverse directions not drawn that are orthogonal to this picture. We imagine we're an observer that lives in region A, we don't have access to region B. In a spatial site, in initial value surface at time 0, I draw, it's not drawn on the slide, but I draw a horizontal line that represents the initial value surface. And then I would thicken the part that we observe and leave thinner the part we don't observe. And that would be a picture we had before, where we deduced the density matrix for this division of space-time. The left and right wedges are often called Rindler wedges. So we consider the density matrix rho sub psi. So psi and omega are two states. And we consider the density matrix of those two states reduced to region A. That means we only consider measurements in region A. And so the density matrix we consider are density matrices appropriate to an observer in region A. The density matrix of the vacuum I call sigma omega, and we know what it is because we computed it before. It was the exponential of -2 pi times the Lorentz boost generator. The density matrix of rho is something, and we don't know what it is. We won't use any property except complete generalities. The relative entropy between them measures how well psi and omega can be distinguished by someone who only makes measurements in region A. And the only property of them that we'll use is that this relative entropy is non-negative. For brevity, I'll use the language of density matrices. A rigorous formulation of what I'm about to say uses von Neumann algebras instead. So here's the definition of relative entropy between two density matrices. Now, when we go to quantum field theory, this relative entropy is actually finite, but written this way, it's a difference of two ultraviolet divergent terms. So it's possible, as Cassini did, to add and subtract a constant to write the relative entropy as a sum of two terms that are both ultraviolet finite. That's obviously a better thing to do. So when we do this, well, we'll discuss the two terms separately. First, I'll discuss this one. Here, trace rho log rho is minus the fine-grained or entanglement entropy of the state psi with the density matrix rho, and trace sigma log sigma is minus the entanglement entropy of the vacuum. Also, for observations, in each case, the entanglement entropy for observations only in the right Rindler wedge A. So entanglement entropies, as I told you, are divergent in quantum field theory, but differences of entanglement entropies are typically finite. That's because every state looks like the vacuum at short distances and has the same short distance divergences as the vacuum. So this difference of entanglement entropies is the entanglement entropy of the vacuum minus the entanglement entropy of the state psi. And Cassini, let's call it minus delta S. Delta S is the extra entanglement in the state psi compared to the entanglement in the vacuum. So the area law divergence has canceled out when we take this difference. Now let's evaluate the other term, which was trace of rho sigma log sigma minus the trace of rho log sigma. We have to remember that if O is any operator, then its expectation value in a state is the trace of sigma times O, where sigma is the density matrix for state psi, or likewise for state chi, we would use the density matrix for state chi. Now we showed before, Now we showed before that, we showed before that the density matrix of the vacuum was e to the minus 2 pi k. So minus, we're going to take O, the operator, to be minus the logarithm of the density matrix of the vacuum. And in view of our formula for sigma, that means that minus the log of sigma is 2 pi times the Lorentz boost generator, which is 2 pi times that integral. So this term is a matrix element of log sigma in the vacuum minus a matrix element of log sigma for the state chi. And there's an overall minus sign. There's not an overall minus sign, but there's a minus sign when we go to k, because minus log sigma is 2 pi k. So this term comes out to be 2 pi times the expectation value of the boost generator in the state psi minus 2 pi times the same thing in the vacuum. But writing the standard formula for the boost generator, we get this for the first contribution. The vacuum expectation value of the energy density is ultraviolet divergent, but with the usual regularization, the corresponding expectation in the vacuum vanishes, so I haven't written it. But with any regularization, this difference is independent of the regularization. It's the difference between the expectation value of the boost generator in the state psi and in the vacuum. So now let's define curly E as the expectation value of the boost generator in the state psi. Cassini's insight was that if psi is a quantum state that describes a system that intuitively is localized almost entirely in the region A where X is positive, and this system has size R and energy E, then curly E is at least as big as E times R. In other words, if you know what's meant by the size and energy of a system, and that the system is localized at positive X, then you'd say that this integral within a factor of order 1 is at least the size of the system times its energy. He therefore proposed to use the quantity curly E, which is rigorously defined for all quantum states, as the stand-in for Bekenstein's heuristic E times R. And he proposed delta S, the difference in entanglement entropies between the state psi and the vacuum state omega, to stand in for the heuristic entropy in the Bekenstein proposal. The positivity of relative entropy says that the sum of the two terms is non-negative. So it says that the energy is equal to or bigger than the entropy difference over 2 pi, with equality only if psi equals omega. That's Cassini's rigorous version of the Bekenstein bound, valid for all quantum states. Now, to illustrate the subtlety, I'd like to tell you the following. It's possible for both the left and right-hand side to be negative, because it's possible to have a quantum state whose entanglement in the vacuum is less than that of the vacuum, whose entanglement in the Rindler wedge is less than that of the vacuum. It's also possible to have a quantum state where this integral in the Rindler wedge is negative. So both the energy and the entropy in the Bekenstein bound can be negative, but nevertheless, the inequality is always true. So Cassini he interpreted correctly and proved the Bekenstein bound. And to do that, he had to interpret the terms in ways that go far beyond the thermodynamic reasoning, the thermodynamic framework in which the heuristic statements of Bekenstein had made sense. That's why it took 28 years from Bekenstein's proposal for the bound till the rigorous interpretation and proof. In conclusion, I reviewed some of the early developments in black hole thermodynamics in the 70s. I hope I've given you at least a taste of how in modern flavor, the subject has gotten a very different flavor that requires understanding quantum entropy in a way that makes sense for all states, whether thermodynamics is valid or not. If I had more time in the first half of the talk, I would have wanted to describe the Euclidean approach to black hole entropy pioneered by Gibbons and Hawking, with important contributions by others. In the second half of the talk, I would have wanted to explain Aaron Wall's proof of the generalized second law, the Ryu Takenagi holographic formula for entanglement entropy, the notion of entanglement wedge reconstruction, and the role of quantum error correction in holography. But not today, unfortunately. Thank you very much. I'll just conclude by saying that I chose the topic because I consider the modern developments genuinely very exciting and probably pointing to something really new. I regret I was only able to explain the first result pointing to these modern developments. Even if I'd gotten through this complete list, which I very naively thought I was going to do when I started to prepare the talk, it would not have brought us up to date. It still would have given you the subject as of 5 or 6 years ago. Thank you.
Thanks a lot. Ed, for a fantastic talk. Though you say you weren't able to explain everything you wanted to, I think it's amazing how much you did explain very clearly.
Well, I worry a little bit, to be honest with you, for the students or anyone who hasn't been exposed to the subject before. I wanted to start at the beginning because I thought if I only told the modern stuff, that would mean that half the audience would be totally lost at the beginning. But squeezing as much as I did in one lecture, I'm worried it was too much. But anyway, tried.
Wonderful. Now, we can take questions now. So I propose the following mechanism for doing so. If you'd like to ask a question, please raise your hand using the raise hand feature on Zoom. And I'll call on people as I see their hands. Okay. Spenta, please ask your question.
Can you hear me?
Yes.
Yes.
Yeah. Well, I mean, it's a request. Can we have a follow-up talk at some point?
Well, we run
fantastic. It'll be
we
fantastic.
run a quantum space-time lecture series, and if you're willing, Ed, we would be very, very happy to have you give a follow-up of this as part of our seminar series. Any Friday that works for you.
I'll be happy to do that at some point.
Wonderful. Thank you.
But the only thing is, am I allowed to assume that that the audience has reviewed this lecture or is familiar with it?
Yes, I think so. I think so.
I think that I would want to start where this one ended.
Yes.
It's hopeful. If one starts and explains the background again, I'd get the same thing would happen.
Yes, I propose that you assume that everyone has attended this lecture and then we follow up.
Okay.
Yes.
Fine.
I'll be in touch with you about that.
Fantastic. Thank you so much.
Sandeep.
Yeah, Edward, I wanted to say it was a really beautiful tour de force. I mean, fantastic. And, very inspiring as always. But my question to you was, it was so striking that just the positivity of relative entropy brought us this result.
Yes.
And I hadn't realized this, I'm embarrassed to say, till you discussed the result. And I just wanted, even though you don't have the time, if you could just give us a glimpse for, in terms of some of the other inequalities and so on, just a little bit. I mean, is relative entropy powerful enough? Are there key new concepts? Sorry, just 2 minutes.
Well, I won't be able to explain the proof, but I'll tell you what the second topic would have been. The second topic would have been Aaron Well's proof of the generalized second law. So Bekenstein had proposed the generalized second law. Okay, what is the generalized second law? So, well, maybe I should go back to where I had a picture of the black hole horizon. So you consider something falling across the black hole horizon. I want to say that its area over 4G increases by more than the entropy that fell behind the horizon. Well, if the black hole classically was growing, then this is going to be trivial because you'd have a classical growth in the area, which would overwhelm a quantum correction. But the interesting case is to consider a black hole that classically is static, but it's interacting with quantum fields outside the black hole. Classically, nothing is happening if the area is constant, but quantum mechanically, there are quantum fields here. Well, there might be a few stray photons or something. Okay, suppose the black hole absorbs a single photon. We have the same problem that we had in the Bekenstein bounds. We want its area to go up by more than its entropy went down. But what was the entropy of a single photon outside the black hole? So as a completely general statement, the second law doesn't seem to make sense. But following Cassini, Aaron Well showed that you could formulate and prove the generalized second law, provided you interpret the entropy of a single photon in terms of the entanglement entropy of everything outside the black hole. And then he gave a completely general proof of the second law, but he required another inequality for relative entropy, which is that it's monotonic. So that means it increases if you increase the area in which you make measurements.
Oh, I see.
I think that should be part of the next lecture, but the topic, at least, is that the generalized second law is something that, again, only makes sense if you use fine-grained entropy.
I see. So sorry, the monotonicity of relative entropy under inclusion, is that is if you take a smaller.
Yeah, well, if you take a bigger region, it increases. A smaller region, it goes down.
Yeah.
And I'd like to tell you that I was very dissatisfied that physicists were using the monotonicity of relative entropy and not knowing how to prove it. So I actually wrote my version. Well, I didn't do anything originally except try to write it in a way that would be appealing to quantum field theorists. But I wrote my version of the proof in my notes on entanglement entropy.
Yeah.
So anyone who wants to do homework before the second lecture,
yes,
you could look at just, I think, the third section of that article.
Yeah, I see. Okay.
Now, well, let me tell you what the second subject would be in the next lecture. So Bekenstein and Hawking entropy of a black hole was thermodynamic entropy. It increases. So entropy that obeys a generalized second law is thermodynamic entropy.
Mm-hmm.
Von Neumann entropy under evolution of a quantum system is constant, because an isolated quantum system changes by unitary evolution, and the density matrix changes, but the entropy does not.
Correct.
So another topic in the next lecture would be in gravity, what's the analog of the Bekenstein-Hawking entropy for the fine-grained entropy of a black hole, the thing that doesn't change.
I see.
Okay, but I don't want to do too much of this now because we want to leave something for the lecture.
Yeah, I see. Okay, thank you very much.
Sure.
Shiraz, you're muted.
Sorry, TP, you should be able to, please go ahead.
Yeah. Thank you. So from a quantum theoretic viewpoint, how can we understand as to why the entropy is increasing as area rather than the volume? Must gravity necessarily come in at this stage to explain holographic behavior of the entropy?
Well, first of all, we don't know deep answers to the first question, but surely gravity is necessary for any version of holography. And yes, in quantum field theory, we would not get an entropy bounded by the area. So the answer to your question broadly is it must be true, but we don't understand it very concretely.
Thank you.
Sorry.
Because you were on mute again.
Yeah, sorry. I see two more questions. The first is by a participant named ABCD on Zoom. So ABCD, please ask your question. ABCD, you're muted. Oh, I have to unmute. Sorry, I have to allow you to ask. Yeah, you should be able to talk now.
I think he got muted again.
Okay. Okay. I'm promoting to panelists, so you should ABCD. You should be able to talk now.
Oh, it's probably me. I wanted to ask the meaning of relative entropy, even if it's just in terms of classical probabilities, because it's just not a norm. Otherwise, it would be symmetric in its argument, right?
Yes. So I think the question is the following. The question was, let's say classically, why is relative entropy a good concept? Let's see if I can draw. Okay. So the definition is a little odd because it's asymmetrical. It has a nice intuitive interpretation. You have a hypothesis that a system is described by a density matrix sigma, but it's really described by rho. You're wrong. See, that question is asymmetrical between rho and sigma. Sigma is your hypothesis, rho is the correct answer. Then the question is, in a measurement, for some reason I can't draw anymore, but all right, imagine I've closed that parenthesis. in a measurement, how well can you learn that your hypothesis is wrong if the correct answer is sigma? The answer is if you make n trials, provided n times the relative entropy is large, you'll be able to exclude your initial hypothesis. You can read that as a classical statement in any introduction to information theory. Again, I wrote my version of it. You can find online my mini introduction to information theory, where I explain this, but everyone else who writes about information theory does also. It's also true quantum mechanically. So quantum mechanically, and my notes also have a part of that quantum mechanically. If sigma is the correct density matrix of the system, if sigma is your hypothesis about the density matrix, rho is the correct answer, and you're given n copies, can you, by a measurement, learn that your initial hypothesis is wrong? The ability to do so is controlled by the value of the relative entropy. If n times the relative entropy is large, you'll be able to learn that your initial hypothesis was wrong.
Right. Okay. Yeah. Thanks.
Okay. Any more questions? I don't see any more raised hands.
Hello, am I audible?
Hello? Barely, sort of in a very warped way. Who is this, please? You can try to speak again, please. I didn't see who you were. Okay, perhaps I can, while we're waiting, perhaps I can ask a question, Ed. As you mentioned earlier, entanglement entropies across the surface in the quantum field theory have an ultraviolet divergence.
Yes.
And that ultraviolet divergence is proportional to the area. And you mentioned at some point in your lecture the hope that gravity would cut off this ultraviolet divergence and reproduce this idea of Wheeler. I wanted to ask whether the recent progress throws light on that question.
Well, it encourages the idea, because I'd say that all the results that have been obtained are consistent with the idea that something like that is true. But I'd say we've learned more about what properties a quantum gravity theory should have. So, for example, it's clear now that a lot of the paradoxes about quantum black holes are resolved in a theory that has entanglement wedge reconstruction and the Ryu-Takanagi formula for the entropy. But we don't know concretely such a theory. I'm not sure if I've been responsive to your question or not.
Okay, so perhaps I can ask again. There was this old idea that that the divergences that cause the entanglement entropy are all tightly related to to renormalization of Newton's constant.
Oh yes, well,
and that when you account for both of these, that gives you a finite entropy. I mean, makes sense of A by 4G.
That's a true statement, perturbatively at least. It probably needs a little explanation. Gosh. Well, for some reason at the moment I'm not able to draw on the slide, but when you say the area over 4 times Newton's constant has ultraviolet divergences. Then you add to it the entropy. If you try to interpret the entropy as entanglement entropy, that also has ultraviolet divergences. However, Susskind and Uglum made a very simple observation that the sum of the area over 4G plus the entropy is better defined than either one is separately, because the ultraviolet divergences cancel in the two. Perhaps that's what you're getting at.
Yes, so I wanted to So is this part of what encourages this idea that?
Yes, that's certainly one of the things that does. Right. That encourages. Yes.
Okay. I suppose I'll ask a clearer question at the end of your second talk,
Well, the question is clear. I just don't have much to say about it. So no one can do a first principles calculation of entanglement entropy getting the right answer. But it is true that you can argue fairly convincingly that the area over 4G plus the entropy outside is ultraviolet finite. Okay. I'm actually getting confused at the moment why you can't calculate it. Sorry. Okay. So I think the situation is the following, Chaz.
Yes.
You can calculate the quantum corrections to A over 4G, meaning the normalization of G, and that matches the ultraviolet divergence in the entropy. What you can't explain is why the classical part of A over 4G was an entropy.
Okay.
So you can show that when things change, A over 4G plus the entropy behaves in a sensible fashion. The root of the problem is that A over 4G is of order 1 over h bar, so it should be a classical effect. Whereas when you compute a quantum contribution to the entropy, it's of order h bar to the 0 from a one-loop diagram. An L-loop diagram is proportional to h bar to the L minus 1. I said h bar to 1, but the Bekenstein-Hawking entropy is of order 1 over h bar. So it's an L-loop effect with L equals 0. We don't have a framework for interpreting a classical effect as an entropy. Actually, nothing's been said of note, I don't think, except something else that was said, I believe, by Susskind and Uglum, which is that in string theory, the loop corrections come from Riemann surfaces of genus G, but the classical action comes from a Riemann surface of genus 0. So string theory, actually, compared to ordinary quantum field theory, is a framework where the classical action and the corrections are on the same footing. And in particular, Susskind and Uglum proposed that the genus 0, the 1 over h bar contribution to the entanglement entropy simply came from a spherical worldsheet that was partly in one Rensselaer wedge and partly in the other. I'd say that qualitatively that's probably true for weakly coupled string theory, but no one's been able to make it concrete.
Thank you very much. Okay, so I don't see any further questions. So let's thank Ed again for a fantastic talk and look forward to the to the follow-up. I'll be in touch with Ed and we'll fix a schedule and I'll send out an email about the next talk. Ed, I'll also request you to send me the slides of your talk, if that's okay. We can put them up on our webpage and so that people can read these slides as preparation for the next talk. They haven't been able to get it.
Well, sure. Okay.
Thank you.
Thank you
so much for a fantastic talk.
Thank you very, very much. That was very